Okay. Okay, so in today's class, we're going to introduce you to the analysis of algorithms. There is a very classical book. That's what the picture shows here, Introduction to Algorithms, written by a couple of authors. The lead author is Corman. And I believe I've referred to this book before in the slides in week 1 for the software engineering, where not the software engineering, for the overview of data structures, I believe. But anyway, this textbook is classical. It's one of the best textbooks out there about algorithms. So I'm borrowing some of their slides to explain sort of the foundation of analysis of algorithms. And I hope this is going to be useful to you. And the textbook in chapter 20, I believe it's chapter 20, chapter 18 in our textbook. It explains a little bit about the analysis. It introduces you some searching and sorting, and also, some introduction of some of the similar material that I'm going to introduce to you. But I think this is a better way of, explaining this to you. But we're going to also look into the book a little bit, but probably not today, but it'll be left as a homework for you guys to review. All right, let's get into this. Now, after this little lecture, we're going to actually spend a little time about the midterm, all right? Okay. Now, the analysis of algorithms, what this is about. Now, we all know what the algorithm is, right? An algorithm is essentially a procedural, step-by-step procedure to solve a problem computationally. With a computer. That's sort of the idea is, this is how we solve a problem with a computer. So your algorithm is essentially a way to tell the computer how to solve a problem. And this is a very active field of study in computer science. And now some of the algorithms are classical. So we always want to introduce the classical stuff to get you introduced to some of the concepts here. And this is even about searching and sorting problems. They are still very active today. It's like people are still trying to find algorithms. They're optimized in different situations. And so anyway, why is it important to actually study algorithms and actually specifically their performance? Well, first of all, want the algorithm to complete, right? Cannot be an algorithm that runs forever is not good in practice, has no practical use. If it runs forever, it never finishes. And if you don't, produce a good algorithm, it may just run forever, right? Of course, it depends on the speed of your program. So now, besides performance, what's more important? So here we have a list of what's more important than performance when we think about algorithm. In reality, when you do really software engineering, when you write a program with a team, a real application, you have to think about modularity. Is this program modular so that it's easy to maintain and every module is well tested? And perhaps the modules can be reused. Those are some of the software engineering concerns. Is it correct? Okay, maybe it's really fast, but is it correct? But actually, we'll see. Well, not necessarily in this lecture. We'll see. Actually, sometimes an algorithm may give you approximate result, but that's good enough. Not necessarily 100% correct, but that's also. But most of the time, we're going to talk about algorithm needs to produce the right results. And then, is it maintainable? Maintainability, in addition to modularity, which helps with maintainability, but also the clarity. Your code, is it clear to understand? And because when we're talking about maintenance of a code, you may not, if you're the person that wrote the original code, you may not be the one that keeps maintaining it. So you want to make sure your code actually communicates its intent, perhaps with the comments, appropriate comments, to the other engineers that might be maintaining the code. And then we'll also talk about functionality. that may be important to the user, but not necessarily that important to when you talk about a core algorithm. Robust. Why is it robust? In the sense that what if there's a failure scenario that one of the one of the steps actually throws an exception. Are you handling it? What if you make a network call that times out? And what is your way of handling that situation? So is it robust to handle? Is it fault tolerant? And then is it user friendly? Yes. Essentially, if your module is going to be used by other programmers, it's like a library that people want to use. Is it going to be easy to use? Right. So these are all really the concerns, some things that you may consider still important. Right. You say, okay, performance is important, but these are the other issues that are also important. And then programmer time, is the programmer, efficient in producing the code and also maintaining it? And is it a simple, easy to understand? Is it going to be extensible? Because is your algorithm rigid so that nobody can adapt it for different uses? Is it going to be reliable? That it won't crash, right? If the input size is very large, say I have an array of 1,000,000 elements, can your algorithm sort it, right? For example. So these are all really the concerns if you write a program, and the algorithm it's not just about performance. There's other things, but then in this particular lecture, we're going to focus on performance. So algorithm really help us understand scalability. In what sense? Well, if an algorithm is performant, that means that it's going to be able to handle a large input as the input size grows, and they should be able to handle that increasing growth in this input to be able to produce appropriate output. And if it's efficient, if it's actually performant. If the performance is not bad, maybe when the size grows to a certain level, then the algorithm doesn't really perform well. It may just crash, or it may just be really, really slow. It runs for days and then it doesn't finish. And so the algorithmic mathematics, right, actually is a language for talking about program behavior. Now, what does that mean? So essentially, it's a way when you analyze. So when we talk about here, the analysis, we're going to be touching a little bit about mathematics. It's a little bit sort of deviating from a very practice-oriented approach for a couple of weeks, right? For the first half of this course. Now, this is we're talking a little bit about the theory and specifically more of a mathematics behind algorithms, and really to analyze what's the program, how this program is going to behave as the input size grows. So we kind of always talk about the behavior where, when the input size is small, fine. Doesn't matter how performant your algorithm is, you're probably going to be able to cope with it. But if the input size is huge, as it grows, can your algorithm, scale with it? So the performance we're talking about is essentially it's the currency of computing. And currency of computing is essentially now performance. There's actually different ways to measure performance. And usually it's about running time. Not necessarily in absolute terms, because on the same computer, depending on how many programs you're running currently, how much leftover capacity that's used, like a memory or CPU is going to impact how fast your program runs. So even during different time of day when you run, it's going to produce different kind of running time. But we're not necessarily so concerned about the absolute time. And then, of course, if you're running on your laptop versus another supercomputer, and it's going to be much faster than a supercomputer, right? So because you have different computing capacity. However, the performance is really still key here when we talk about, let's say you're going to run your program in the cloud. So if your program is more performant, you're going to reduce the bill for your cloud usage. You're going to be using less computing resources. All the computing resources are charged or metered. So that is it. That's really what we'll talk about performance. Let's consider a very classical problem of sorting. We have an input. It's a sequence of n numbers. and we want to produce an output, which is a permutation of the input numbers such that they form a ordering. So you have the first number, no greater than the second number. Suppose we're ordering in a non-decreasing order, right? Maybe you can do a non-increasing order, but there's a non-decreasing order. So A1 prime less than equal to A2 prime. So here's a more concrete example here, right? So the input, we have these numbers 8, 2, 4, 9, 3, 6. So we want to produce an output that's sorted. So 2, 3, 4, 6, 8, 9. So it's a very simple problem. I think everybody understands it. So consider an algorithm here. This algorithm is one of the classical sorting algorithms, not necessarily the best one if we think about performance, but this is one of the ones that can be easily understood. The algorithm here, written here, it's called a pseudocode. This is not C++, it's not C, it's not Java, it's not whatever in every language, but it has similarities, right? We can easily understand it. So some of the symbols, just to explain, right? The pseudocode, this left arrow means assignment, okay? So this convention is more of adopted from, I would say, kind of like assembly language usage. But anyway, it's just a symbol. This indicates we're going to assign 2 to n to this symbol j in a for loop, okay? The input to this particular procedure is you have an array of n elements. Now, notice here, we're using one-based indexing, not zero-based indexing in most programming languages. Now, because we use one indexed array here, because it's easier when we communicate, talk about an algorithm in natural language, it's just, our minds start with one, just easier to handle. So this is why typically in this pseudocode that we see, we start with one. But when you really implement this into a particular program language, you either, adapt, change those indexes so that your handle's starting from 0, or you may just waste the very first cell and, just say the very first element, 0th element is not going to be used. You can do that too, right? So anyway, but when it comes to pseudocode, this is when we analyze an algorithm, we want to use a pseudocode, not to be bogged down with the language specifics and getting this grammatically correct. This is more of a communication for analysis on paper, okay? So we have a for loop here. Now, here's a very simple way to understand insertion sort. So you play cards. I think most people play cards when you get take the cards from the deck. Let's say you put them in a sorted order. You start with basically let's say 1, 2, 3, 4, 5, right? You kind of just lay that out in your hand. Let's say you want to put in a sorted order, so it's easier for you to look at. So when you draw the first card, you put it into your hand. That first card is sorted, right? There's one card, it's sorted. You draw the next card. If it is bigger than this first card, you put this next to it to the right, right? If it's smaller, what you just draw is smaller, then you insert into the left-hand side of it. And now you have 2 cards in the hand that's sorted, right? So now you draw the third card and you compare, starting from the right, which is the largest number in your hand. Your hand always holds a portion of the array that's already sorted, right? Now you got this new card, where do you want to put it? You have to find the right place to insert it in the order. So you're starting from the right hand side, checking the biggest element. Is this element, bigger than what you're drawing, the card you want to insert? If it's a bigger, and then you move on to the left, and then check the next one. Is it bigger? If it's still bigger, then you move to the left until you find a one that's smaller, and then and then you put this card right next to the right side of the smaller card, and then you put this card in the right order, so they're all still sorted. So that is basically the idea. And this algorithm, let's see. Actually, let's take a look at the idea with an abstraction, just in a little. So let's say you have this array arranged in memory, right, from first element to the nth element. And we're not using 0 here, but just easier for our mind to consume, analyze. And you have maintain 2 indexes here. The J index is the outer loop. And this J index is essentially the card we just draw from the deck, okay? So you start from this, let's say, your left side, you're determining where to insert J. The card you just draw, you want to insert into your hand. The cards that's already sorted in your left hand. That's what it means here. So I want to use that analogy so you can picture. So, and then let's say we're going to assign the value of J to key. We'll call this key. And this is the value you want to compare and determine where to sort, where to insert. Is this 3, 4, 5, or is the ace king, right? So you want to decide where to put in. So then we're going to compare with these elements here, which is tracked by I, right? So I, we start from J minus 1. So we start from the element that's the rightmost element that's in the left hand. We start from that largest element. That, remember, this part is always sorted. So if that value is greater than key, then we'll keep looking to the left. Okay, now when we keep looking to the left, what we'll also do is we're going to move. We're actually sorting in place, meaning we're not using a different array to a copy. We're going to move elements so they're being sorted in the end. So we move the element of the I, because I was greater than the key, right? That value is greater than key, so we'll move this to the right. Thinking of this like your hand is holding this card that you just draw, you want to figure out where to put it, then you slide to the left and then compare with the next card, right? So you have to move that AI to the AI plus 1, meaning that just move this element to the right, and now you're going to compare with the next value. So I, we're going to reduce I, so we're going to look at the value that's with a lower index, the card right next to it, is on the left, okay? So we'll keep doing this. In this illustration, we have these 4 elements that are all bigger than the key. Until we find this element here, we realize, okay, that AI is less than or equal to key, no longer bigger, right? This is how it exits this inner loop. So then we know we're gonna put the key right at the AI plus 1, because the AI, remember the AI was less than or equal to key, so we'll put this key in the slot that's to the right of I. Okay, so we're not touching I, but we're putting the key into the I plus 1. That's where we need to insert it. Remember, that location was vacated because we'll move that element in the previous iteration of that while loop here. We'll move that to the right. Okay, the original location for J was already occupied in the first time when we compared the element to the rightmost in the left hand, and we determined that was greater than that key, then the AJ. So we'll move that to occupy J. So now we'll put that key, insert into that I plus 1 location. That's where it's supposed to be. So it will continue to be sorted. Now we have sorted this portion with 1 more element. And then we'll keep going from, starting from J equal to 2. Remember, we draw the first card. That first card, 1 card in the hand, that's sorted by itself, right? So that's why we start from 2 and go all the way to the end for every element. So we figure out, this is the right-hand side are the cards from the deck that have not drawn. You have not drawn, and so we're basically, taking 1 from the top and then put this into the left hand. That's the illustration here. Now, any question here? Understand that concept?
No, right now.
Yeah, got it.
No, yeah. Professor,
Okay.
you no, forget it.
Okay. All right. So now let's look at a little more concrete illustration. So we have this array of 6 elements here, right? They are not sorted. So what's going to happen? First, we're going to starting with the j from this element, starting from the index 2, okay? This is index 1. And this index 1 starting out, this one element is sorted. So we're going to determine where to place this 2. So we compare it to the left, and then we determine, okay, this is a greater than that, so we're going to move this to the right, move 8 to the right, 1 by 1 slot, and then we place 2 into it because it went out of the boundary. Remember that algorithm here, we also have another condition, I greater than 0. So that's why, you know, in the beginning, it's going to just place right here, the 0 plus 1 in the place in that slot 1. Now we have 2 and A sorted. So we're going to move on to 4. And then we determine where to put the 4. Well, 4 is less than 8. So we'll move A to the right. And then we compare with the 2, but realize also it's greater than 2. So this is the right place to be. And then we're going to determine where 9 goes. And it looks like 9 is greater than 8. So it stays in the same place. So we're going to look at 3. Same thing, goes to, you know, it starts comparing with the 9 and with the A and then with the 4 and then with 2 is greater than 2 and it goes to the right side of 2. So that's basically where it goes. And then the very last element, 6, same thing, as less than 9, less than 8, greater than 4 goes here. Okay, remember we're moving the elements to the right. Gonna shift this to the right so that 6 is inserted right here. Okay. So this is the insertion sort. Now let's analyze the running time. So we realize that actually there's 2 loops inside. There's outer loop, there's the inner loop. Outer loop runs for a certain number of times. It's actually n minus 1, right? From 2 to n. And the inner loop, it depends on which element we're inserting is, you know, there's a certain number of iterations that we're doing as well, but it's not always n times. So now there's one thing to notice, your running time of this algorithm depends on the input. Imagine if your input array is already sorted. That would be pretty easy to sort. Your algorithm can run on a sorted array. In this case, with the insertion sort, imagine this whole thing was already sorted. That means, imagine, let's say this is the array we're going to sort. Okay, this is the input into the insertion sort. So the algorithm still runs. So it starts from this 3, and the 3 is going to compare with the 2, it stays in the same place. 4 compare with the 3, it stays in the same place, and so on, right? So we're still examining the n minus 1 elements. They will be done. There's actually no movements, essentially. So, but then what happens if, now imagine, what happens if this array is reverse sorted? You know, if it's reverse sorted, what happens is every time when you compare to determine where your J element goes, when you're doing insertion, you have to go all the way to the left, right? Like the longest distance. So that's considered worst case scenario. So now we see the running time actually depends on the inputs. Now, however, normally we're more interested in the upper bound, like worst case scenario, how much time is going to take. And so if we know this is how much time it's going to take in the worst case scenario, then all the scenarios is not going to exceed that much time, right? So that's why we typically like to analyze the upper bounds. So we just talk about the worst case. If the input array is reverse sorted, that would be worst case for this algorithm. Now, an average case is when we need to consider all the inputs. Like An instance of input is basically an array of given numbers. Now we cannot anticipate what the inputs are, right? To analyze an average case, we'll have to make an assumption about the statistical distribution of the inputs, right? How often is going to be, sorted or reverse sorted or just random, right? And then if you do that assumption of a statistical distribution, then you can calculate an expected time with the statistics. We're not going to do a whole lot of analysis here, but just know that this is one of the things that people may analyze for average case scenario. And the best case scenario, honestly, is not worth mentioning. It's just not very insightful if we just know, hey, best case is this is how much it's going to perform. You may have a terrible algorithm that performs really well in the best case scenario, right? Let's say you have best case scenario, this array is already sorted, then we can cheat and the algorithm will do nothing. It's already sorted, so I'm not doing anything if I know what the input is, right? So it's not practical. So we're always actually usually more interested in this worst case scenario, which will give us the upper bound on the running time. Now, see, pictures like how's my picture now? Is it frozen?
Yeah,
Still
I don't
frozen?
know. No, no anymore.
But it was frozen sometimes from time to time?
Yeah.
Oh, okay. As the software is a little flimsy. All right, sorry about that. Maybe it has to do with the network. Okay. So machine dependent time, as we talked about earlier, the actual worst case running time depends on the speed of your computer. Could it be the relative speed on the same machine, different time, because you have other things running, you may get different results. Could it be also the absolute speed when you compare with different machines? You can come up with different numbers because different machines have different computing resources. So those are going to be sort of difficult to talk about. Now, what's usually more interesting here is we want to ignore the machine-dependent constants, like because this CPU, this computer has 6 core, 8 core, that kind of stuff. Or maybe and by the way, when we analyze the algorithm, talking about that performance, we typically want to think about with this sort of a model of computing. We don't want to consider the parallel computing. We want to say, it's computed sequentially. What's the worst case scenario, right? Because if you leverage the parallel computing, then you're not getting a very decent analysis because that parallelism, it's that's another dimension. It's orthogonal to how we analyze the performance of if your program is just running single-threaded sequentially, not multi-threaded, or not multi-process, or not multi-computer in a parallel networked situation. So there's a distributed application. There's many ways in real life to speed up an algorithm. Like thinking about, for example, like just think of a Tesla example, right? They have this autonomous driving. There's a lot of algorithms behind the scenes, but of course they have to speed up to the level where it has to be able to compute, make a decision, go left or right in an instant before it gets into an accident. And so in that case, it's going to use a ton of parallel computing mechanisms and distributed computing, and has many computers computing in the backs behind the scene, perhaps using some kind of a divide and conquer mechanism. I'm going to mention about the divide and conquer algorithm technique. And but here, generally speaking, we want to analyze assuming the algorithm is running on a single process in a single thread, right? So we also want to remove that machine-dependent constants. Some machines are faster or slower, but we're more concerned with the growth of the running time. When the input size grows, approaching infinity, right? So here, the input size n, in the case of our insertion sort, is the number of elements in the array, number of elements we need to sort. That would be the input size. Now, depending on the problem, the input size could be represented in a different way. But in this sorting situation, sorting problem, it's pretty clear. The input size, we're talking about the number of elements. That's what matters. So when n grows, we want to analyze how does this algorithm behave in terms of running time. This is what we're interested in most of the time. And so that particular analysis is called asymptotic analysis, actually. Asymptotic analysis is the term to describe looking at the growth of a function as the sort of the input to that function, grows, and want to see how the function grows. That's the asymptotic behavior we're looking at. Now let's look at one notation. There are many notations. We're going to introduce you to more, but in today's lecture, we're going to just look at theta. There's a Greek letter theta here. So theta notation. Now theta of g of n, here's a mathematical definition of theta. Theta of g of n, a function g of n, is actually a set of functions. And this set of functions satisfy a particular condition. What condition? The condition is all the functions in this set that belong to this theta is bounded by g of n, just with a constant difference. When the n is big enough, that's really what this means. Interpreting what this means, when the n is big enough, ignore the small n's, at some point, okay, as this n grows, at some point, this later part of this function, thinking of this rendered function in a xy coordinate system, this function fn, whatever those things are bounded by g of n with a constant multiplier. So that's really what this means. So this theta, what this allows us to do is we want to ignore the insignificant constants. We just want to analyze the growth, right, of the g of n. That we say, well, if your running time is within this set, for example, here's an example. Let's say the running time of your algorithm is this formula. Is a 3n cubed plus 90n squared minus 5n plus 6046. Okay, let's say this is the running time for your algorithm. Now, how do we analyze that running time? If you really want to add things up, like as an example, right? Let's go back to, so you would analyze, okay, so for this statement, this is going to be a constant operation. So it's going to be a C1 time, right? I don't really care. We're talking about a second or a millisecond. I don't know. It doesn't really matter. It's a constant, right? So this is a constant. And this assignment is another constant. And then you have a loop, right? So these constants will be looped over for n times. So when you add all this time, you can substitute a specific time with just a constant, and then add them up. See how much time your algorithm actually takes to complete, right? You add them up, considering all the loops and stuff. And then that's what you get. Imagine, let's just say, this is what we get. Let's say we get this formula, okay? N is the size of the array. And then, so we will write to say this equals to, it's a little weird, theta of n cubed. Now, why is it weird? Because theta is actually a set of functions, right? I mean, how can a function be equal to another set of functions? It's not, so we're kind of abusing this symbol a little bit, the equal sign here. Really what it means is like, is within that mathematical symbol within set, right? But we write this with the equal sign. Simply, it's a notational abuse, but which is okay, accepted. So we're saying ignore those lower order terms, because when the n grows large enough, this n cubed term is going to dominate the value of a whole function. So that's really what this means. So we're saying this actually is this particular function, according to this definition, right, it will be bounded by this n cubed within a constant difference multiply C1, C2, right? So this Fn, imagine this is going to be basically this will be within the set of theta of n cubed. That's really what this means. But the reason we write it this way is we simplify our analysis because we don't really care about this constant, the coefficients. Those things don't really matter anymore. And when the n grows large enough, those things really don't matter anymore. This is like what we're concerned about. Okay. Now, okay, so here, when we say when the n gets large enough, imagine if you have an algorithm that takes theta of n squared time, that algorithm will always beat a theta of n cubed algorithm. Okay, so imagine this is actually, this is running time. Of course, the lower the better, right? So this is say it's this theta n squared, and this blue line is theta n cubed. As you see, the cube is going to grow faster in terms of running time, so it's going to be slower, right? So, but then they may just cross path at some point. You know, when it's lower, maybe it's some kind of curve, and we don't care. But at some point, once the n is big enough, at n0, at some point, we actually normally don't even care at what point, but we just know that at some point that this n squared is going to be growing slower than n cubed. Okay, so this is what we're interested in when we look at the algorithm in terms of the asymptotic performance. Now, it does not mean we should just ignore, like, okay, let's say you got an algorithm of n, theta of n squared, but then you also got another algorithm theta of n cubed. But it doesn't mean that theta of n cubed has no value. Sometimes it still has a value. We don't just want to ignore that because the real world design has other considerations. In the beginning, we have a whole list of things that could be more important than performance. So, but it's just a way for us to structure our thinking, okay? So back to our insertion sort. Now, so here, we're just giving this out as the, now this is a very simple way to think about this. The running time, T of n, for insertion sort is actually a summation, right? Now, you see j equal to n of through n, from to 2 through n. Remember that is the outer for loop. Essentially, that's the card we draw from the deck. So that many times happened. Now, in each iteration of that outer for loop, we have a while loop inside. Remember that algorithm, right? It's only a few lines. Inside of it, we need to decide where that J goes. The card is in our hand. We need to figure out where to insert. So we remember our hand is sorted with J elements in our hand. Well, actually J minus 1, right? So remember, if we're determining where the second element to go, we have one card in our hand that we may potentially compare with. If j equal to 2, we may compare, if that's j equal to 3, then we'll have two cards that are sorted in the hand. At the most, we're going to compare with the two of them. So that's why in the inside of the loop, it's actually theta of j, well, j minus 1, right? That's how many, well, never mind. It's still j times that while loop, even though let's say in the most we compare with the j minus 1 elements, but the operation for that loop, we still actually do one more time, and then it will exit out of the loop, right? Like we increase or we decrease I, or do a comparison. So essentially it's a one more time. So the theta of j. So this is essentially like the running time if we really analyze in that way. And this actually can be solved mathematically. It's actually arithmetic series. Yeah, remember, 1 plus 2 plus 3 plus 4 until plus n, and that equals to n times n minus plus 1 divided by 2, right? So we know that can be solved. And when you have that polynomial, the highest order term is n squared, essentially. So this is why, remember how we use this example. If the highest order term is n squared, essentially it's going to be theta of n squared. That's the running time. And now, actually, keep in mind though, this bound is a tight band from both upper and lower. Remember the definition here. This g of n bounds all the things that are inside the running time, all the functions that potentially have different coefficients or constants. Is actually bounded from both upper and lower. So a theta is a tight bound for both upper and lower. And we're going to look at the other notations. They're going to be only talking about upper bound or lower bound later on, okay? So in the average case scenario, the intuition here we'll talk about is that on the average case, let's just say half of the deck is already sorted when you just take this into your hand, right? And so if you think of that way, the well, no, not half a sorted, sorry. So it's actually saying for every time when you actually need to compare to decide where to insert that J card, let's just say it only needs to go half of the way. Compare half of what's already in your left hand, the sorted hand, only half of it you need to compare. You don't go all the way to the very end, which is the worst case, or you don't go just not going anywhere at all. You don't have to move as the best case because the whole thing is already sorted. Then, let's say you have to go halfway. Let's just say that's the average case. So it's kind of the intuition here. This can be analyzed mathematically, but so this is the intuition. I want to explain this to you. So it would be J divided by 2, theta of that. Now, as we know, this constant doesn't really matter. It won't impact the resulting summation. So it's still going to be n squared. Now, is insertion sort a fast algorithm? It's considered moderately so. It's not the fastest. We'll look at some other algorithm later on that will be faster. And when n grows, we also realize when n grows large, the insertion sort is inefficient. It's slow. Now, there's another algorithm. It's pretty elegant algorithm, actually. And we'll see, actually this algorithm will be faster. We'll see why. This algorithm is very simple to understand. And now we're given an array of n elements, okay? So the very first step is we check if n equal to 1. If n equal to 1, right, we're talking about an array of size of a 1. If your array has only one element, we're done. This array is sorted, right? You have one element, that one element is sorted. No work to be done. Now, if it's not a 1, it's greater than 1, well, which is most of the case, probably. When that is the case, we're going to actually recursively sort the first half and the second half. We split this array in the middle. Now remember, this is natural numbers. If you have odd number of elements, say 3 elements, you divide it by 1 element, 2 elements, right? If you have 4 elements in total, you divide 2 and 2. So that's why we're using the ceiling here, right? We're using the ceiling here just to make sure this is it comes down to an integer. So we're splitting basically in the middle, and we're going to sort the first half. Recursively means we're going to invoke this same procedure, merge sort, on the first half, as well as on the second half, okay? And then once these 2 arrays are sorted, now we know this is going to sort it. Assume this is what the function does, is going to sort it. So we're going to call that function again on this. and on the half of it, and another half of it, we'll sort these two halves separately. And the third step is to merge these two halves into a single list. There's two sorted lists, we need to merge them. So as you see, I mean, this is a no-brainer, no work to be done, super simple. Here, we just simply invoke merge sort on the first half and merge sort on the second half, easy. So really the key part here is the merge process. Let's see how the merge is done. Now, assume we have the first half sorted, right? 2, 7, 13, 20. Second half sorted as well, 1, 9, 11, 12. What we're going to do to merge, so we look at for each array, we're going to look at essentially the first element. Okay, so we're going to just compare these two first elements. Which one is smaller? We realize one is smaller, right? So we take one, put this into the newly allocated space. One is going to be here. And then once we have taken one, what's remaining for the right-hand side array, we have a remaining 9, 11, 12, right? One is taken. We have that taken out of this array. So of course, in the algorithm implementation, you have to keep track of where it is, right? By indexes. But so let's say this is where this first element now is. Now just imagine this one is taken out, okay? So now we're gonna start with this element from the right-hand side, the second array, and the first array still will do comparing with the 2. So now we're gonna compare 2 and 9. Which one is smaller? Is 2. So now we're gonna take 2 as well. So remember here at the bottom, we're forming a new array here. This will be sorted, right? So each time we pick the smaller element out of the 2. So we take 2 out. Now the left array has 7, 13, 20 remaining. And then between 7 and 9, 7 is smaller, so we're gonna take 7. Okay, now we have 20, 13 remaining for the left array. And now 9 is smaller, so we take 9. Okay, now we have 13, 20 for the left-hand side. The right-hand side will have 11, 12. And the 11 is smaller, we take 11. Okay, now we're gonna compare this right-hand side only has one element left, which is 12. Compare that with the first element of the left-hand side, and we see 12 is smaller, we take 12. Once I've taken 12, there's no right-hand side, there's nothing left. We know the remaining portion of the left-hand side of the array is already sorted. Remember, we start with the sorted 2 halves. And so we just simply take the rest of it and put that in the end. So now we have a new combined sorted list, right? So this is how this merging process works. Now remember this algorithm has a stopping condition. So remember when we split this in half, we're gonna keep splitting. In the end, we're gonna have an array of size 1, right? You got it down to array size of a 2, and then we'll split it to 1 and 1. If it got down to size 3, we'll split into 1 and 2. So once it becomes 1, that 1, it's sorted. So see how that goes? So it's a recursive call. And then assuming an average case, we have some numbers of elements in both sides, both halves, and then we're gonna do, this is the merging process, okay? So the merging process, as we can easily see, for every number, we only basically do a one comparison. So you see for every number, for number 1, we have done one comparison. Number 2, well, actually number 2, we'll do another comparison with another side, but anyway, so we examine, the point is that we examine each element basically just one time when we pick the numbers into another combined array. And so this sorting process just takes about theta of n to merge that n elements. So when we talk about if it's theta of n, that's a linear function, right? So the highest order is n. That's a linear function, so it's called a linear time. We usually say it takes a linear time to merge two sorted arrays. Now, let's analyze this merge sort in this particular algorithm. And so we want to know the T of n for this merge sort algorithm. Now, this first case, when n equal to 1, sorting one array of size 1, that's a constant time. Constant time will represent with theta of 1. Now, this, by the way, it says it's abuse. You know, it seems does not make a whole lot of sense, but it's a notation. It's just remember this for what it is. It's a notation telling you this is a constant time. We don't know how much time, but it's just a constant time. It does not grow according to your size, input size n. When the input size n grows, this statement is always the same. You know, it's a constant time. That's what it means. Theta of 1. Okay, and this recursive sorting. Now we know to sort this half array. It's just basically, well, now we know sorting the whole size of n is T of n, right? So we do recursively here. You know, the time to take to sort half of this, it would be T of n divided by 2, right? Half of n. And then we have 2 halves to sort. So it'll be 2 times that running time, okay? So then the last statement is basically a merge process, so which we already analyzed. That takes theta of n time. So we also represent this thing here. So now there's a notation here. This part about sorting half of them, it's really, there's actually a ceiling function here, but the ceiling or the floor function perhaps, it doesn't really matter when it comes to asymptotic analysis. That minor difference usually would be ignored. It's equivalent to talking about n divided by 2. Okay, it's insignificant when n grows large enough. So we can look at this T of n in this particular format. We'll call this a recurrence. A recurrence means that when you analyze the time of a function, forget about time, whatever it is, a function, the value of a function n, T of n, it depends on, it's basically broken down into, is analyzed in terms of the smaller value, smaller input value. You're breaking down a larger problem into smaller problems. That's called a recurrence. By solving a large problem, you solve the smaller problems, and you somehow combine them to solve your final large problem. So in this case, this is the how much time is going to take if n is greater than 1. When n equal to 1 is theta of 1, a constant. So this is usually how we represent. Now this recurrence is, this is basically the total running time for this merge sort algorithm. Now we can solve that, by the way. This can be solved in multiple ways. Now at this time, we're not gonna look at how this is solved. And I think in the next lecture, maybe we'll look at one of the methods to see how this is solved. But right now, actually, we can already look at one way though. This is one of the ways to use a recursion tree. It's called a recursion tree in the sense that, just think of, now, recursive call. Remember, this function merge sort is calling a merge sort itself on a smaller input size. So total time of T of n for the top level n elements, we're going to break this down into essentially, remember that it takes, you know, basically there is a constant time. Remember the constant time for, you know, this particular formula here. So actually go the theta of n. We're going to just represent this with a Cn, right? The theta of n is it's a set of functions, right? So the current definition of theta. So we're going to just use a constant coefficient, and the Cn as represented this actually how much time it takes there. So instead of your theta notation here, we're going to use the actual time here. So this is Cn for some number C, okay? And then that Cn is actually the constant part of that calculation, remember the part where we break it into two arrays, but then we still have to solve these two arrays. Well, not just two arrays, but also the combining part of it, right? We're breaking them and the combining in the end. And that all of that time is consolidated. Let's say they are calculated into this there. This is what Cn is represented for. But not only this, we still have another portion of the time we have not, considered. The other portion of the time is that the sorting the subarray, the two halves, the t of n, half of n, right? So there's two of them. So we kind of present that in a sort of a tree format. So just sort of visual representation. We still need to sort two subarrays. And then they represent it as a t of n divided by 2 as the time, right? We know, let's say, assuming the total times t of n. Now, for each of those smaller problems, remember the analysis is the same as we just analyzed from the very top with n elements. Now, essentially, the difference is with half of elements, half of n elements. So it's the same thing. The constant part of it takes this much time, Cn divided by 2. And then, but then there's also the two even smaller problems we need to solve. The smaller problems, now they divide another half. So there's only a quarter left, right? For each subarray is a quarter. So we have 2 quarters to solve for each side. So we're breaking down a bigger problem into smaller problems. And that goes on until we got down to the leaf where a problem is small enough becomes just basically an array of size 1. We know by cutting that array by half and by cutting this continually, it's going to come down to an array of size 1, right? And that array of size 1 is sorted, and that takes just a constant time to sort. I mean, that's really no brainer here. So they're all going to come down to essentially like that in the end by keep dividing it. Now this tree, we know the height of this tree, how many levels are there by dividing this each time by half. This is very simple to calculate. Essentially, this is going to be it's going to be logarithm base 2 of n, right? We are, this is we're going to actually talk a little more about trees later on as a data structure. But for right now, just perhaps I'm not going to explain too much here, but the height, this is a kind of well-known fact, is going to be a log of n. In fact, there's a log of base 2 of n. So this is the height of the tree. And then at each level, have you noticed that each level, the time takes is a Cn. Now remember, the T of n is actually the total, everything, all the nodes in this tree added up, okay? Everything added up, that's the T of n. That's how we broke it down, representing this T of n. We'll kind of, break down this larger problem into smaller problems. So this is actually almost like a trace in the algorithm, how the algorithm works, which is a recursive call. And so we see this level adds up to Cn. This level, so these two adds together is also Cn. And this level is also Cn. In fact, every level is Cn. And the very end, we have n leaves. It's just basically a theta of n. They are not necessarily Cn, but it's just another constant time, a linear time. It's a theta of n. So now we know the height is this much. So essentially, it's the ending result. Now remember this Cn, that's also theta of n, right? Every level is a theta of n. We'll add all them up. So how many are there for theta of n? How many levels is log of n, right? So essentially the running time for this merge sort is log of n times n, right? Essentially this is theta of n times log of n, right? There's this many times of theta of n. This is theta of n. And then so just a little mathematics, it goes down to this is actually the running time, n log of n. Now, n log of n is faster than n squared. So it's actually a more efficient algorithm than the insertion sort. Okay, so we actually, if you plot it in some graphing tool, you'll actually see at some point n log of n grows slower than n squared. N squared goes higher. So that means it grows faster and the algorithm is slower. So we'll say the merge sort asymptotically beats insertion sort in the worst case. And so also we actually notice in the practice when the size n grows to more than 30, usually merge sort beats the insertion sort. Okay. So that's what I wanted to cover today for this lecture. And in Wednesday, we're going to cover the rest of the asymptotic notations and perhaps a little more about analyzing the recurrences. And here we're looking at a recursion tree as one way to analyze it. So this is a pretty classical way of analyzing algorithms, and it's a very, very interesting. So we're gonna, I hope this kind of makes sense. Let me stop the recording and we're gonna actually go, well, actually, you know what? I'll do a separate recording for the midterm. So I'm gonna start recording right now, okay?